Good morning, my dear friends. See now we will go to the another problem. Okay, I will read the problem now. The I section shown in figure is pre-tensioned and used over an effective span of 8 meter. Okay, the span of the beam is 8 meter, and it is an I section as shown in this figure. Okay, determine the extreme fiber stresses at the central section at a transfer of pre-stress. This is very important. Please try to understand. He has asked you to find out the stresses at the central section at a transfer of pre-stress and at working load of 2600 Newton per meter. Okay. The pre-stressing steel consists of 8 wires of 7 mm 5. Okay. The unit stress at transfer is 1000 Newton per mm square. And the loss ratio, he says that it is 0.8. See now, he has given this figure. Okay, all the dimensions of the beam he has given is an I section. Okay, flange is 300 mm by 80 mm, and bottom flange is 200 mm by 100 mm, and the web's dimension is now 180 by 80 mm. Okay, these are the dimensions which he has given. Okay, so now as you see, it is an unsymmetrical section. Okay, and also he has kept here in sense now steel 8 wires of 7 mm 5. 8 wires means 1 2 3 4 5 6 7 8. 8 wires are there, and these 2 wires are placed at 20 mm from the top. Okay, and these 2 wires are placed at 25 plus 25 mm, in sense now 50 mm, and these 4 wires are placed at 25 mm from the bottom. Okay, so he has given all the details like this now. Okay, so now Baba, now the first point here is now since it is an unsymmetrical section, first of all I have to find out where CGC lies. Okay, so to find out this CGC, I have to take and then to find this CGC, I have to take the moments about the top. Okay, so you know how to find out the CGC. Okay, the equation is y bar is equal to sigma y dA divided by sigma dA. Okay, so now how to find out is now I will take now this one now. The area, in sense, first it is dA. dA means it is the area. Area is 300 mm into 80 mm. This is the area of this flange. Okay, so it is 300 mm by 80 mm. Okay, and its CG, in sense I am taking the moments about the top. Okay, its CG lies here now, and its lever arm is 40 mm. Am I right? 80 mm divided by 2. 40 mm is the lever arm. Okay, I am taking the moment of this area about the top. Okay, it's like that only. It is the moment of this area. dA means area, and y is the lever arm. Okay, sigma means it is the summation of all these areas. Okay, so 300 into 80 into 40 mm plus, now I will come to this area now. Okay, it is 180 mm into 80 mm is the area. 180 into 80 mm into its lever arm. Its CG lies here now. From here to here you can easily calculate the lever arm. Okay, so it is 180, it will not 170 it will become. Then the last one, area is 200 into 100 mm. 200 mm into 100 mm is the area, into lever arm is from this point to this. Okay, I think that also you can easily calculate it, divided by sigma dA. Sigma dA means is the summation of all the areas. Okay, this area plus this area plus this area. Okay, all these areas I have written it here now. 300 mm into 80 plus 180 into 80 plus 200 into 100. Okay, so that will give me y bar as 164.52 mm from the top, because I am taking the moments from the top. Am I right? So now from the top, okay, in sense now CGC lies at a distance of 164.5 mm. Am I right? So this is your y bar. Okay, sir. Now CGC lies here, not at the mid center. Okay, so this is your y bar value. As you have calculated, y bar value is now 164.52 from the top. Okay, so from here to here it is now y bar. Baba, this y bar itself I can call it as yt. Am I right now? This is the top fiber stress. In the top fiber it is now, extreme fiber. Yt itself is now 165.5. Baba, once you know Yt, I think Yb can be now easily calculated, because this entire depth is 360 mm. Am I right now? 360 minus this 164.5 will give me your Yb. Am I right now? So automatically Yt and Yb are fixed now. Am I right now? Yt and Yb are fixed. Okay. So now, well, once you know Yt and Yb, I think now area can be now easily calculated. It is the summation of all those three rectangles. Okay, it will give me so much. Okay, area. But now another important thing is now I have to calculate the moment of inertia, I. Moment of inertia of this entire thing. But here I am going to use this formula. Capital Igxx is equal to, it is a small Igxx plus Ah bar square. Baba, this I don't explain you now. If I start explaining you now, it will take more time. Okay, let us assume that you can calculate this I by using this equation. Okay, so now I will go to now to find out the CG of steel group. CGS I have to find out. See now, some steel is here, some steel is here, and some steel is here. So now I have to find out CGS where it lies. Okay, let us assume that area of this steel is 1 unity. Okay, so 1 into, in a sense, I will again taking the moments about the top. Okay, of all steel I will take the moment about the top. See now, 1 into 20 plus again one more is there now, 2. It is 2 into 20. Am I right? So it is now 2 into 20 plus again 2 are here now. 2 into this distance. Am I right? You can easily calculate. So that distance is 310, and again 4. 1, 2, 3, 4. 4 into this distance. Okay. So I think you can easily do it, divided by sigma dA. It is 2 plus 2 plus 4. It is 250 mm from the top. In a sense, CGS lies at 250 mm from the top. In the sense, your CGS is here now, 250 mm from the top. Your CGC is now here, 164.5. Okay. So now, in sense, now the eccentricity is the distance between CGC and CGS. Am I right now? This is the eccentricity. Baba, I think you can easily calculate this eccentricity. It is 250 minus this YT will give me the eccentricity E. Am I right now? So eccentricity can be now easily calculated. Eccentricity is 250 minus 164.5, 85.5 mm. Okay. And since this CGS is below CGC, I have to assign a negative sign for this eccentricity. Okay. So E is minus 85.5 mm. Am I right now? So now here you have to find your CGC, your CGS, then you have to find your eccentricity. Okay. This is one step. Now I will try to now calculate self-weight of the beam now. Okay. Self-weight of the beam, in sense, you know the area you have already calculated, cross-sectional area into 1 meter along the span of the beam. It will give me the volume into density of your concrete will give me your WD, dead load UDL. Okay. And he says that a live load acting on the beam is 2600 Newton per meter. Okay. So WD I know, WL I know. I think MD you can easily calculate. Dead load moment, it is a WD L square by 8. WD is here, span is 8. Okay. So you can easily calculate this much. Similarly, ML can be now easily calculated. Live load moment, it is WL L square by 8. WL is now here, span you know. Okay. ML can be now easily calculated. Okay. So now, but now very important thing what you have to learn here is now, Baba, he has asked you to find out. See now, I will read this problem. Okay. Determine the extreme fiber stresses at the central section at transfer of pre-stress and at the working load of 2600. In a sense, he has asked you to find out the top fiber stress and bottom fiber stress at two instances. One is at a transfer of pre-stress. Baba, when the transfer of pre-stress takes place, okay, I say that it is the initial pre-stress. Am I right now? Initial pre-stress. Baba, he says that initial pre-stress is Fs is equal to 1000 Newton per mm square. Am I right now? Here he has given in the problem, just see here now, stress at transfer, unit stress at transfer is 1000 Newton per mm square. Am I right now? So he has given Fs, it is the pre-stress. Okay, now I want initial pre-stressing force. Baba, F. Baba, force can be given by stress into area. Stress is Fs 1000, As is this stress is acting on this much area of steel. Area of steel is 8 wires are there. Each wire's diameter is now 7 mm. So now area of each wire into 8. This will give me As. Am I right now? Total area of steel it is now. Because each wire diameter is now 7 mm. Am I right? So pi d square by 4 will give me the area of one wire. Such 8 wires are there. Am I right? Into 8. So now this will give me total area of steel. So area of steel into Fs will give me the pre-stressing force. It is the initial pre-stressing force. So initial pre-stressing force is this much. So but now whenever the transfer of pre-stress takes place, in a sense, just whenever I transfer the pre-stress, I anchor the cables, okay, then at that time, Baba, your live load is still, it is not acting. Live load is not acting. And your pre-stressing force is in the initial state. Am I right now? So now I can write top fiber stress Ft as F by A plus or minus Fe Yt by I plus or minus Md Yt by I. Baba, here only dead load is now acting. No live load is now acting. No live load is now acting during the transfer of pre-stress. Am I right now? So now only here these three terms will come. Baba, F, you know all the values. Initial pre-stressing value is now 3078 something. Okay, you know area. Again, F is known to you. Eccentricity is minus 85.5. You already calculated. And Yt also you have calculated. Yt is plus 164.5 divided by I, moment of inertia. Similarly, Md you know. Okay, Yt you know, I you know. Okay, so top fiber stress Ft works out to be plus 2.49. Plus sign indicates that it is compression. Similarly, bottom fiber stress Fb, it is F by A plus or minus Fe Yb by I plus or minus Md Yb by I. Baba, only change from here to here is Yb is now minus 195.9. Am I right, sir? So now fill all the values. You will get Yb value as now plus 8.58. Okay, plus sign indicates that it is compression. So now here top fiber stress also you know it is 2.49. Okay, I have drawn the stress distribution diagram. 2.49, it is a plus. Fb is plus 8.58. So it is plus 8.58. So the stress distribution diagram is like this now. Okay, so now this is how you can find out the stresses in at transfer of pre-stress. But now he has asked you to find out the stresses at the working load. Baba, at working load means when the live load starts acting on the beam. Live load starts acting on the beam. Okay, so now here your Ft is, your Mt will come now. It is Md Yt by I plus Ml Yt by I, or Md plus Ml together I can write it as now Mt. Okay, also another important thing is now, Baba, now here when the live load acts on the beam, your pre-stress will undergo some loss. Okay, it will undergo some loss. And in the problem he has given that, okay, see now, loss ratio eta is 0.8 he has given. Am I right now? He has given the loss ratio as 0.8. So now you can, now I want to find out the effective pre-stress. So now I have to use something called effective pre-stress. Baba, in the last class you have seen effective pre-stress is given by eta times initial pre-stress. Eta I know and initial pre-stressing force also I know. Baba, this will give me final pre-stress or the effective pre-stress. Okay, effective pre-stress is eta f and its value is this much. Okay, and total bending moment mt is, because it is md plus ml now. Okay, md plus ml can be added up to get mt value. Okay, so now you can write tough fiber stress ft is equal to eta f by a. Baba, it is now, it is not f simply. Now at the working load, your pre-stressing force has undergone some loss. Okay, so it is effective pre-stress. So this effective pre-stress eta f, I am going to keep it here now. Eta f by a plus or minus eta f e yt by I plus or minus mt yt by I, because now it is live load also acts on the beam. It is md yt by I plus or minus ml yt by I. Otherwise, I can write directly mt yt by I. Baba, you know all the values. Eta f value you know, it is so much. Area you know, again eta f is so much. Eccentricity you know, yt you know, I you know, mt you know, everything you know. Okay, so your ft works out to be plus 6.39. Again it is plus and indicates that it is compression. Okay, similarly you can find out, Baba, now your fb also know, bottom fiber stress also. The only change with respect to your bottom fiber stress is, okay, here yb value has to be put, and yb value is now minus 195.5. Okay, so if you put, you will get the answer as 1.62. Okay, so the stress distribution diagram can be drawn like this. Okay, thank you very much.